Hello. So I would like to briefly talk about energy motivations to search for deeper physics. So recently, especially thanks to the top AI models like Fable, they are now able to analyze, perform and analyze simulations of given Lagrangian candidate, and for example, in this benchmark, testing various properties of physics. If our model achieves these properties, this is very difficult to get such validation, but at least one model can handle. Um, what are the motivations? The basic ones are to resolve problems. So, for example, the quantum gravity unification, but also the EMC effect, for example, that we don't understand nuclear physics. That quarks work for proton neutron, but for nuclei they tried an EMC effect so they don't work. So currently we have this huge standard model Lagrangian, very general, which fitted parameters, but then there is separate nuclear physics, which there is no connections in this moment. So the second set of huge equations to be fitted to experiment. So then to simplify, yeah. So instead of this huge Lagrangian or two, try to derive it from the deeper theorem. Also the parameters, they are like 30 parameters. We like to derive it from a few. Understand field configurations. I think this is the most important. That it seems the topology is crucial for various situations like nuclear physics, plasma. Currently it's nearly neglected. So we should get better understanding and try to include them in simulations. So now I'd like to talk about potential practical motivations from an energy perspective. Yeah, so one is hot fusion, which is claimed for since the like 1950s that it will be in 20 years, and hopefully this time they are right. But there are many problems, so like these plasma instabilities, so they need better understanding. And for example, in Sans Corona, they see this one-dimensional structure, these shining lines I'm showing in a moment, and there are suggestions that they are topological. So, but now we don't understand them, and maybe they should be included in the simulations to get better and to finally reach this hot fusion practical, maybe in 20 years. The second and third are more controversial, but we could at least try to understand them, and they are extremely promising. This is big risk, high risk, high reward type of topics. So one is the question is, could we get fusion in much lower temperature? So in theory, getting it, we could get a car which has like 1,000 kilometers range per gram of fuel. So sounds great, but the question is it possible? So there are many claims, but there is no reproducibility. Many large players work there, like US Navy, like 100 persons working in this field. There are some suggestions like observe tritium from volcanoes, but the question is how to get it. And the problem is that we have two let's say, protons, and we'd like to fuse them, but they repel by the Coulomb force. So to avoid it, screen this Coulomb repulsion, we could try to put negative charge between them. So one is possibility is muon, so this is called muon catalyzed fusion. But even better would be have just electron, which are everywhere, but the problem is to localize them between the two nuclei. And the electron back scattering seems a promising approach that electron scatters from one nuclei, and electrons but need the same angle. So if such electron would scatter multiple times between two nuclei, then it could screen it down to fusion. Yeah. So the goal would be optimizing parameters like the lattice, electromagnetic wave, sound wave, to increase the probability of such electron scattering multiple times between two nuclei, which needs better understanding. Current, I think, is insufficient. So finally, the third, the most the highest energy, but also the most controversial, the science fiction approach is stimulated proton decay. So proton decay is not. They are trying to search for it in these large water tanks without success, but its suggestions are, for example, in baryogenesis, that after Big Bang, the world created more baryons than antibaryons. The second suggestion is Hawking radiation, that we could, in theory, squeeze matter baryons into black hole, and gather the black hole, this Hawking radiation from evaporation, which is massless, so it has no baryon. So this way you destroy the baryons and gather nearly entire energy, like 100 more higher density than fusion from any matter. So it would be great, but the question is, so how to squeeze matter into black hole is probably completely impractical. But if it can be done through black hole, maybe there is also there could be a direct way. Yeah, so we found black hole try to simulate proton decay. Yeah, so maybe for example we have colliders, maybe try to optimize parameters, maybe polarization, maybe some electromagnetic waves simultaneously. So having a very good model of protons, we could try to simulate this kind of process and maybe try to optimize the parameters, and maybe in 100 years make it practical or not. So let me now briefly talk about why I think that topology is crucial to understand, for example, both nuclear physics, but also the plasma, to understand better, to get better understanding of this plasma instabilities to finally reach practical fusion. So for nuclear physics, I think the best suggestion is that are halonuclei, that we have a core like lithium-11, and let's say two neutrons, can be also protons, in very large distance, like 5 femtometers. So this is like many times larger than of nuclear force. But they are very stable and in so-called Borromean way, that if we remove one, second would also fall apart. So they look like knots. And there are many suggestions that there are indeed some one-dimensional structures, this may be topological between them. And there are suggestions also for the structure in various scales, also cosmic. So there are some observed these filaments, galactic filaments by these pulsar timing arrays. Then cosmic strings finally. But also already in some corona of our sun, they see these shining lines and they release energy by reconnections like shortening. And they don't really understand what makes them stable, but there are suggestions that might be topological. So yes, we should finally understand this topology, which makes stable this in Sun's corona and in all scales. Also, there are suggestions that maybe various types of like Cooper paste in superconductor may also need these one-dimensional structures. Yeah, so I think we finally need to understand what's happening there and not just guessing, and what should improve our simulations for plasma and maybe reach practical fusion in 20 years, hopefully, finally. So the second is much more controversial, but also if successful, would be completely revolution, like this car going 1,000 kilometers per gram of fuel. If only possible, so the question is, so most people say it's not impossible, but there is large societies pursuing it, also by high players. So again, I think we need better understanding and try to verify is it possible or not, finally, and if possible, maybe try to reach it. So if it's possible, then I think that the only way to reach it practically would be that there is some screening. So between these two nuclei, like protons, there is a muon or electron. So one is this muon stimulated catalyzed fusion, and even better would be with electron. But to make electron localized between two protons, seems we need this backscattering, that there is this known effect that electron approaches nuclei and goes back in the same angle. So having two nuclei, there could be electron which makes multiple such backscatterings, and finally allowing them to fuse against the Coulomb repulsion, because there is electron attracting both between. Yeah, so but it needs very precise simulations. We don't really understand now. To optimize parameters, for example, by lattice, by electromagnetic waves, by sound, to increase the probability of such multiple backscatterings of electron between two nuclei. Yeah, so I think we need better understanding of physics for practical simulations to optimize parameters. So finally, this more science fiction approach is trying to stimulate the proton decay. Yeah, so if successful, we are talking about 100 times higher energies, the density from any matter. So it will be completely revolution, like 100,000 kilometers for a car per 1 gram of fuel. So So generally, we don't know if the baryon number can be violated, but for example, there is no Gauss law. So electromagnetic charge cannot be violated because of the Gauss law. But for baryon number, we don't have Gauss law, so maybe it's possible. And there are at least two hypothetical phenomena requiring violation of baryon number conservation. One is baryogenesis, that from Big Bang there was created more matter than antimatter. We know it's true. So the question is where this imbalance comes from. Second is Hawking radiation. That in theory, again, the black hole should evaporate. It has to be massless, so it cannot be baryons. Yeah. So finally, we take baryons, squeeze them into black hole, and gather the energy from evaporation. In theory, we should get nearly MC square and full energy, but it's collapsing into black hole is extremely difficult. So the question is, could we do it directly, avoiding this phase of black hole? So they search for proton decay in this huge room temperature water, not finding anything. But the two examples, baryogenesis and Hawking radiation, use extreme conditions, while in temperature water, maybe we just need more extreme conditions to reach this process. We should search maybe in LHC, and they start to do it. So where to search for it in nature? So for example, center of neutron star has close conditions to black hole, the closest we know, and there are objects which are much brighter than expected. So we don't understand the energy source. So maybe again we should consider that there is a baryon number violation, the kind of birthday baryons. So the question is, could we reach it? So again, we need very good models of nuclei. For example, there are many suggestions that to see nuclei as knots of these topological vortices. So for example, here we can see why proton is lighter than neutron because this external vortex modifies the central charge toward hedgehog, and hedgehog is elementary charge. So proton just enclose this hedgehog while neutron has to compensate it, explaining what is costly, explaining why it's heavier. So if so, we would need to kind of swing this central hedgehog charge to untie this knot. Yeah. So the question is how to do it. Maybe we could try to do it simulations of using various electromagnetic wave, maybe colliders. So generally, having a better model, there is a way to at least try to ask this question. And so is proton decay possible, and if so, how to try to approach it, and maybe 100 years we will be able to reach it. So there are many more arguments to search for deeper physics, but these are just the basic energy motivation, but there could be also many more practical and some unknowns, yeah, so that we are not aware that there could be such possibility in this moment. So I hope, yeah, so I hope, especially with help of artificial intelligence, we soon go to the deeper level and resolve many problems, and also reach the practical applications like in nuclear energy physics. Thank you for attention.